now let's jump into the details of neuromorphic electronic circuits. I told you that we are in the business of building chips. And building these things, you saw very nice examples of hardware implementations of these neural networks, spiky neural networks. And the first thing that, of course, we are competing with the world of deep networks. Everyone can simulate neural networks really efficiently. You know, with Tegra, NVIDIA, which is only 30 watts, you can really implement very complex neural networks and solve lots and lots of problems, even spiky neural networks, and there's many companies doing this. So people always ask, why do you go to the trouble of building chips when you can simulate everything on even now low power? You're again competing with the steamroller of Moore's law. And the idea is that we really try to want to understand what the principles of computation, we heard about the principles of computation that the brain is using by using neural networks. And the reason we build hardware is that we can really build systems that work in the same way of the real brain. And in fact, if we have something that has the same dynamics, the same language using spikes, the same physics, as I will show you, we can actually close the loop. We can connect real neural circuits to silicon neural circuits, and then try to make predictions, have a hypothesis, validate the hypothesis, invalidate them, and close the loop in this way. So also for doing prosthetic devices, brain-machine interfaces, but even just for understanding the basic principles of computation, having a tool that allows you to, in real time, as you're changing knobs, see the effect of that on the real system is extremely valuable. So then you can really change your hypothesis, change the model, and then close this loop. So that's the reason why we're doing this. It goes also, again, back to Caltech, to the original days where Dick Feynman was. And what was left on his blackboard was this nice quote that I like very much. I don't think it's his originally, but it was on his blackboard. What I cannot create, I do not understand. It's this idea of synthetic biology. If you build biological systems, if you just construct them, hopefully it's another way of getting intuition on why it works in that way. So it's not supposed to replace theory or experiments. It's an additional tool in the tool set of a neuroscientist or neuromorphic engineer. And of course, if you're building these things, you can try to reverse engineer. Also, since they are chips and electronic systems, you can try to build things which are useful for practical applications, for society, for making startups and becoming rich. So there's also always this dual aspect, basic research for understanding, but also technology transfer for applying these devices for implementing efficient neural processing systems, which are dedicated. Again, I want to emphasize it's not something that will replace general purpose computing. These are really specialized, the technology is really optimized to do specialized, dedicated processing tasks. Another motivation, this is the last motivation slide I have, is the fact that we are getting, with the IoT, we're putting sensors everywhere in our house, our washing machine, our refrigerator, our scale is getting more and more sensors, and there's more and more data being produced by all of these sensors. And just last February, this year, there was a Nature article saying that big data needs a hardware revolution. If we use the current existing hardware, we're not going to be able to sustain the data and the processing needs that the society is generating. So in 2017, over 10 zettabytes of data were produced, and the IT infrastructure and the consumer electronics that was used to process all of this data was over 10% of the global world electricity supply. If we keep on this pace and we use the standard technologies, by 2025 we'll have 50 billion of IoT devices, which will produce over 180 zettabytes of data, which will lead to a consumption of 1/5 of the global energy. So this is really a serious problem that needs to be addressed, and even Nature is pointing this out. And what I really like about this article here is the fine print. Here, software companies make headlines currently, Google, Facebook, all these companies I showed before. But research on computer hardware could bring bigger rewards. So if you're making startups and you're trying to find the next breakthrough, this is one could. It's a could. It's not will. it's potentially a very interesting market to be, a place where to be, to build these type of hardware that can solve this problem. And so the type of hardware, we've seen some very nice examples just in the previous talk from Karl-Heinz, and I'll go on and tell you more about some alternative, slightly different ways of doing that type of hardware, this neuromorphic VLSI technology. We've already seen this slide here. Brains are different from standard technology, so if we really want to make something that will be able to solve these IoT problems, we have to look at radically different computing paradigms. So we need a radical paradigm shift in computer hardware technologies. That's what this Nature article was saying, and what all the companies around the world, Intel, Texas Instruments, Samsung, everyone realized and is trying to find how to solve. And we know that there is a solution because brains are an existence proof. They can process at very low power densities in very small volumes. You don't need to look at a human brain. You saw, you can even look at a bee brain. In fact, here it is, which is 1 milligram of weight, 1 millimeter cube of volume. It has less than 1 million neurons. And it's using 10 to the minus 15 joules per spike. So it's very, very efficient. And if you look at bees' brains, they're amazing technology. It's a computer that can do massively parallel distributed computation, fine motor control. It can interact in real time with the environment. It has complex spatiotemporal pattern recognition. They can go forage and go back to the nest. It actually has a social behavior. It has a language. And it does all of this with really slow, noisy, and unreliable hardware, the neurons and the synapses. And so speed here is not a requirement. Standard CMOS technology has been always pushing to have faster, smaller transistors. Here we can actually allow ourselves the luxury of having slow components. So for example, organic transistors would be ideal for this. DNA computing might be another. Maybe chemical computing could be another technology. For now, we use CMOS because it's widely available and accessible. But anything that does not require speed, which could lead to compact and low-power hardware, would also be a good candidate for this type of paradigm, this computing paradigm. And we heard even this morning from the Intel CEO that we have to start looking at domain-specific hardware devices, not general-purpose processors, and that hardware and software go together. Well, that's exactly what's happening in the brain. The hardware and the software is the same thing. The way neurons are connected, the way they are structured, the way the synapses are shaped, determines the functionality. That is the software. So that's what we also will show you that we can do with the chips that we build. Together with the radical paradigm shift, we have to realize that if we want to really do something different, we cannot stick to the standard way of doing computation. We've heard John von Neumann mentioned many times. This is the classical John von Neumann bottleneck. It's the architecture in which you have a memory unit, a memory block away from the processing unit, which now is separated into control and ALU, arithmetic logic. And the bottleneck is right here, where you have to shift the data back and forth between memory. There was a nice analogy that a colleague, a friend of mine, Piotr Dudek, made. If you look at standard chips now, one bit is a few nanometers big. If you have the SRAM, it's 6 transistors to store 1 bit. That's a few nanometers, maybe 100 nanometers or 50 nanometers square. Let's assume these 50 nanometers are a box of this size. So that's 1 bit. And what the processor does, standard processors, whenever they process the data, they take the bit and they flip it. You get your box, you turn it around. Then you have to bring it back to CPU. So if you scale things up, this 10 square nanometers, and you look at the wires that go from the CPU to the level 1 cache, the closest thing that's on the chip, you have to walk from here to the coffee break. So you flip your bit, you put it in the coffee break where the coffee machine is, you take the other bit, or you take 8 or 16 of those, you come back here, you flip them, you go back. So you realize that computation is free. Flipping things does not require any energy, a few picojoules. Taking the data back and forth from the memory is what actually consumes memory. That's level 1 cache. If you go to level 2 cache, it's like going to the restaurant. If you go to external memory, it's like going to Lisbon. And if you go to the hard disk, it's going to the United States. So you can imagine how much energy is consumed in only data transfer. And that's why this in-memory computing is becoming so important. And that's why also this, one of the possible in-memory computing paradigms is the brain-inspired or neuromorphic architectures. That's why it's really important. So that's the main difference between shifting memory around in standard von Neumann architectures, and you'll see that memory and computation is co-localized in neural networks. The other part that I emphasized this morning is time. In standard machines, standard processing, time is virtualized, and you only change things when you have a clock cycle, and the clock can be anything. We heard the importance in Karl-Heinz's talk about physical time and computing through time, using the dynamics and the physics of your hardware computing substrate to do computation. That reduces power enormously. And the other point is analog. You know, if you want to do an exponential in silicon, you can use a single transistor to produce an exponential current out of a voltage input. That is the exponential. You're not simulating the exponential. It's like in a supercomputer weather simulation. It does not rain in the supercomputer. You can simulate the rain, but here it is raining. If you want to do an exponential, you have a current which is the exponential. If you want to integrate, you just put a current into a capacitor that is the integral. So it's really emulation. It's not simulation. You're not, you know, discretizing, approximating, running through some clock cycles to get an approximate solution. You really have the physics working for you. And also what Karl-Heinz was pointing out, you know, it's a physical system that also allows you to save huge amounts of power. And I'll show you how we even go one step further by having exactly the same physics, not just using physics to do time processing, but using exactly the same physics of real cells. And finally, slowing down silicon. It's really important to slow down silicon if you want to have a device that can interact with the environment at biological timescales. So if you want to have voice recognition, gesture recognition, if you want to interface to our neurons, we need to have the same time constants so that, you know, the system that's doing the signal processing is optimally matched. It's an optimal filter to the signals coming in. So we need to have, if we want to interact with humans, we need to have human-type time constants of the orders of tens to milliseconds. It's really hard to do this in silicon because silicon likes to go at gigahertz. And so we need to be really careful on how we do these designs. And so now I'm going to show you how we can do it with this neuromorphic. And I just want to remind you that there is now this new wave of neuromorphic computing that became popular in the last 5-10 years. We've heard about the True North chip, the IBM chip, the Intel chip, the Human Brain Project platforms. All of those are really very nice examples of neuromorphic architectures that are dedicated VLSI hardware. They're targeting high-performance computing. They're mainly, at least for the Intel and IBM, mainly application-driven. They're you know, industrial products. And they follow conservative approaches in the sense that they either use standard analog design techniques or digital. For example, IBM has to guarantee that it's bit precise so that the software simulation can be bit by bit matched by the hardware. This is a requirement by the managers of IBM. So this is why they're using conservative approaches. The other school of thought is the one that comes from Caltech from the early 90s, much older, over 20 years. Which is not concerned with selling products. It's really concerned with fundamental research, understanding how the brain works, and using silicon as a tool, just like you would do animal experiments or use MATLAB to do models. And there, again, the word emulation comes here. That's why I was really emphasizing the difference between simulation, which is happening here, for example, in IBM and Intel, with emulation. And to emulate, we really exploit the physics. I'll show you exactly how we do that. And then time again. Here, time is representing itself. If you want to correlate what I'm saying now with what happened 50 milliseconds ago, you can just have a capacitor which is slowly decaying and seeing whether the signals are the same. You don't need to put everything in memory, go get it back, compare the two memory blocks, put them back in memory, and do this shuffling back and forth at very high speed to get these 50 millisecond correlations. So it really saves a lot of power, and it's what natural systems do effortlessly. So to show you what we do in Zurich, we sort of stayed faithful to this line of research. That's where I did some of my postdoc years there. Misha was really influential. She also founded the Institute of Neuroinformatics that is now my institute. And so we really follow this original philosophy. And again, remember, if we want to copy the brain, we really have to understand how it works. So at least 2/3 of the institute now are really only doing fundamental neuroscience. Animal experiments, biology, we study all of the, the complex molecular dynamics. We have to learn about all of the terminology that biology uses. And we really try to understand the principles of computation of the brain because we're interested in computation. So we have to study all the biology part, but we then try to apply that to computer science, computer theory, theory of computation. Of course, because we're building chips, we need to know how to do that as well. So we train our students and we ourselves studying microelectronics and physics. So it's really an interdisciplinary. It's like, I like to think it's like those days in which McCulloch was working with Letvin, with Pitts, and Minsky, different neurophysiologists, with psychologists, with mathematicians, with electrical engineers, everyone under the same roof in this place in Zurich, which I invite all of you to come and visit here. It would be very nice. So once we do the fundamental research, then we try to build these circuits. I will show you what this means, subthreshold analog VLSI. And then we try to build systems out of these circuits. So we have either multiple cores on the chip or multiple chips. And these systems have to communicate. And you learned from this morning that if you have to send analog signals across long distances, at least the way the brain does it is it converts that into spikes, and into a frequency, or into spike timing. We heard that, so spike timing is really important. And that's what we do with the chips as well. That's really the most efficient. If you try to optimize from an engineering point of view, signal communication and maximize signal-to-noise ratios, this is what you end up finding out, that you need to do pulse-frequency modulation. And then, of course, I told you the brain does not make sense, and we even heard from Karl-Heinz this morning, the brain does not make sense if it's not embedded in an environment, and then it produces behavior. The whole purpose of having a brain is to receive inputs, process them, and produce outputs in a closed loop. So when we try to understand if we can make intelligent chips, we put them in agents, whether it's robots or platforms that move, but anything that has sensory input and produces motor output. And then we can try to validate the intelligence of these systems by having this closed loop interaction with the environment. And I'll show you examples where we have that. And this is also where we have continuous learning. So if we have negative feedback, adaptation, and learning, they're all tested in these types of environments here. Please do interrupt me again at any time if you have questions. So we study the brain, we study cortical circuits. This is an example of area 17 of the cat visual cortex. So here you see with, again, the Golgi staining technique, single neurons. These are pyramidal cells. They're called pyramidal because they have this triangular shape. And then we try to build circuits that emulate the physics of proteic channels of these cells. How do we do that? We use basically transistors. This is a symbol of a transistor. You apply an input signal by applying a differential voltage. You put a battery between gate and source, and you measure the output current. And if your input voltage is below the threshold voltage of the transistor, which is a process-dependent parameter, it's just a parameter that is given to you by the foundry, then the transistor works in the so-called subthreshold domain, or weak inversion domain. If it's above, it's in the above threshold domain, or strong inversion domain. And here you see what's going on. If you apply an input voltage, the VGS is the difference between here, which is between 0 and 1 volt, or 0 and 1.2 volts, you have, on a semi-log plot, a line, which means that you have a pure exponential. So you have current, which standard analog designers in the 80s and 90s thought it was just 0 because it's so small. It's between 10 to the minus 14 and then 10 to the minus 6. But you have a huge dynamic range in which you have this exponential current, which goes from femtoamps to microamps with 1 volt. So if you do the power, it's really nanowatts to microwatts. If you go above threshold, the transistors start to behave quadratically, and so on the semi-log plot, that's how you have this saturation. This is the standard way. If you open any textbook and you want to build a hi-fi equipment or any type of analog converter, this is where you use your analog circuit here, where you have milliamps and 5, 4, 3 volts. So you're burning much more power. What you gain here is precision. If you have some noisy input, which is moving around 3 volts, say here, then it's going to move around 3 volts here. Your current is going to jitter very small amount. If you have the same variation in input here around 0.5 volt, your current is going to go all over the place. You're going to be very sensitive to noise. So that's why standard textbooks always work here. This is really something, a no-no. Don't go there if you want to do anything analog. But if you're doing neurons, this is exactly where you want to be. Neurons are exactly as sensitive to noise as these transistors are. On top of that, the reason you have exponentials is because the mechanism of carrier transport that allows the current to go through this channel is diffusion. It's exactly the same mechanism that cells use to push ions inside and outside of the cell through diffusion. You have different concentrations, and you diffuse things in and out. In fact, if you look at what Hodgkin and Huxley, when they got their Nobel Prize, when they were studying the giant squid axon, look at the data that they took in 1952. This is the data that they have from their paper. This is the sodium conductance channel and the potassium conductance channel as a function of change in voltage. Now, this is a conductance, but you know that conductance and current is linearly proportional, so it's equivalent to having a current. So see it here, we have a line on a semi-log plot. Here you have a line on a semi-log plot. We have the same physics. We have Boltzmann statistics, we have diffusion, exponential. So now by using subthreshold, we are emulating the physics of real cells. We're not simulating anything, it's direct emulation. If you want to have diffusion of carriers, which could be ions or electrons, you just apply a differential voltage and you get the same physics. So that's why by using these transistors in this way, we can really reproduce many, if not all, of the properties of real cells, real neurons, real synapses, and many of the things that are happening inside our brain. So that's the main message I want to give you, that we use analog, subthreshold, with picoamps, which also helps us to obtain millisecond time constants. Because if you have a picoamp current and a picofarad capacitor, the two picos simplify out, and you get, there is always the thermal voltage, which is 25 millivolts at room temperature. So 1 picoamp, 1 picofarad gives you 25 milliseconds time constant because of this kT over Q factor, the thermal voltage. So we have realistic time constants, tens of milliseconds, biologically plausible time constants. We have emulation, direct emulations of the physics of cells. Now we can start using these transistors to really build more complex structures and look at learning and the processing of data, inference, reasoning. How do we reason about things? I'm hungry, I see a Coke there, or I'm thirsty, I see a Coke, I go get it. All of these things, I will show you examples on how to do it using transistors and compositions of transistors. But first, I want to show you some examples of models of neurons that then we can then build with transistors. And this is the most important part. This is what Hodgkin and Huxley also proposed, and I showed you already. If you want to model a neuron, and we even saw it from this morning, all you need to do is to have a capacitor, which models the bilipid membrane layer, which is perfect insulator. And then if you want to model the ions flowing through these channels that open and close, you can put resistors or conductances. And if you have just a passive conductance, that's the basic behavior. And if you apply a small input, you get first-order dynamics, as we heard. And then the sodium, the potassium, there's many channels in a neuron that implement different behaviors. The most important ones are the ones we saw this morning for producing the action potential. But there is calcium, and there's all sorts of channels that have different effects. And the more you add, the more you are close to the biophysical reality. And you can do this just by using transistors. So we can have a capacitor, a transistor, maybe some more complicated circuits to have some more flexibility. But you can actually implement all of this in CMOS and build a neuron just by using this analogy. And this analogy also can be modeled with differential equations, of course. You can just write everything as a differential equation and simulate it on a computer. And this is what Hodgkin and Huxley proposed. We've already seen this equation before, but basically this is it. You just have Kirchhoff's current laws and the conservation of energy with the capacitance and the various currents coming in, which could be coming in from the external input, they could be coming in from the synapses, and then they could be coming in or going out from the passive behavior. And all of these currents are governed by some differential equation. And this is what gave Hodgkin and Huxley the Nobel Prize. They figured out what differential equations to use to fit the data of the giant squid axon to this equation here. And these are quite complex. These P and Q are like 1/3 and 1/4, and so you have different dynamics going on. So you can implement those, as I said, in MATLAB, and you can run very, very faithful models of real neurons. And if you show them to a neurophysiologist, they will not be able to tell you the difference between a real neuron output and a simulated neuron output. But we can also put simplified versions of these in CMOS and have a physical circuit that does exactly the same. I told you about the reduced models. Oh, no, I didn't. But there are ways of reducing the models because those are very complicated. And when computers were slow, people tried to reduce the models here. And then you know that there is the very, very reduced version, which is the basic integrate and fire. You sum. If you pass the threshold, you fire, and you reset. That's the most basic. But it's basically a reduced version of these equations. And these were the two camps. 20 years ago, when people were simulating neurons on computers and either spending a lot of time with the faithful differential equations or doing fast simulations with integrate and fire, there were lots of debates. You know, what is the level of abstraction? Are you losing anything if you do simplified models? And only recently, so these debates went on for years and years, both in software and in hardware. You could either do a very complex CMOS circuit or a very simple CMOS circuit, and it was not clear which one was better. And only recently there's been a way to put a bridge between these two schools of thoughts with a so-called generalized integrate and fire model. So it's a simpler equation than Hodgkin and Huxley, but it's been shown that it can reproduce all of the Hodgkin and Huxley behaviors. And so now finally, after years of debates, there is, in the computational neuroscience and in the hardware community, a consensus on what is the best model to use to do neurons. And this was proposed by Gerstner and colleagues. It's called Generalized Integrate and Fire Model, and they showed that it can be a very reliable predictor of real cells. And you know, it really models the dynamics of real cells faithfully. In fact, if you try to see the difference between real data and simulated data, if you zoom in even, you have very small differences. It's very hard to understand which one is the real one, which one is the simulated one. And remember these equations. It's basically an integrate and fire equation, where this is the basic simple equation. The only added term is, well, there are two added terms. This W here, which is a slow variable, and the general function, f of v. So the slow variable is also a differential equation. So this is a coupled system, similar to the original models that were also proposed by Lapic and Rashevsky, and then Wilson and Cowan and others. But the novel part is this function here, which is this gives you the generalized integrate and fire. If you use a quadratic equation, so v squared, ab squared plus bv, etc., this would give rise to what is called the Idzikevich model, because Idzikevich proposed it. It's very nice to use if you're using MATLAB, because in MATLAB, in standard CPUs, it's really fast to simulate squares, quadratic relationships. You just shift bits around, and you can really implement squares really efficiently. In biology, the one that actually is the best one is the exponential. It's not a surprise, because if you expand the exponential with Taylor, you have both the first order, the second order, and then all the other orders. So the Idzikevich is a particular second order approximation of the exponential. So now the most used and most powerful model that exists is called the exponential integrate and fire model. Adaptive exponential. Adaptive because there is this slow variable with a negative feedback term, so it's adaptation. And then exponential because the f is an exponential. So that's just to somehow clear the confusion between the two camps. And now everybody agrees in the community that this ADEXP, adaptive exponential integrate and fire model, is the best one. It's going to be important because I'll show you the circuit that actually does that. And also from the hardware community, everybody somehow independently converged in having implementations one way or another of adaptive exponential integrate and fire models. So much for the neurons. People pretty much agree on how to model them. The community, the hardware, the neuromorphic community agrees on the hardware implementation. Now we move on to the synapses, which I told you now are the stars of the show. We even heard this morning, or just after lunch, the dendritic computation and the synaptic computation is what's really important. And I already showed you this picture. The synapses are really complex, nonlinear computational element that store also memory, so it's also in-memory computing. So this is just a reminder from this morning. And now that we know that we need to put together synapses and neurons, we try to figure out what are the architectures that we should put on chip when we build these chips. And here is an example of a layout of an old chip where I just drew by hand some symbols that represent synapses and neurons. Typically, when we do these chips, we have an array of neurons. Maybe here it's just a line, and then a large collection of synapses. In biology, every neuron has about 10,000 inputs, 10,000 synapses, and 10,000 outputs. It's really large fan in and large fan out. So on chip, we usually have many more synapses than neurons. And what you should really notice is the fact that all of these blocks, these circuits here, which are also shown here, are not just simple resistors and capacitors. In fact, in silicon, it's hard to put resistors. We always put transistors. But they are some complex circuits that have state. They have capacitance, so they can remember what happened shortly before. They have nonlinear dynamics. You can implement short-term plasticity, short-term depression, short-term facilitation. They have adaptation loops, so they can really have long time scales with long time scale adaptation loops, which is called homeostatic plasticity, which can act on hours or even days. And they have spike timing dependent plasticity, basically learning, which changes their weight depending on the spikes coming in and the spikes going out. So the spike timing, that's where it is. And that's how we stimulate these chips. We send spikes in, and we measure spikes out. So whenever you have one of these silicon neurons, you always have to convert whatever signal you have, voice, video, pressure, you have to convert that into spikes. Those go inside the chip, they get processed, and the chip produces spikes in output. So it's a transceiver that receives spikes and transmits spikes. And now, the way you can do computation, how do you use this, is you can connect the output of one neuron, we can do it here, the output of one neuron to the input of another one through outside lookup tables. If it's off-chip, it would be an off-chip lookup table. If it's on-chip, it would be an on-chip router. But basically, by having these lookup tables, you can then create any type of arbitrary network. That's where you get your programmability. How do you program a neural network? Even though everything is analog and it's fixed, once you design the chip, nothing changes. That's only true for the neurons and the synapses. But the network, how you create a network, whether it's recurrent or feed-forward or multi-layer, that can be done by programming the connectivity tables, which are memory, so either router or lookup tables or memory chips. And so that gives you a lot of flexibility because you have low-power analog computation inside the chip, and then you can program the network properties from outside. Again, the structure determines functionality, but the structure is programmable. It could be even evolvable. You can have a software algorithm that changes it at runtime, depending on what cost function you want to minimize. So that's the basic principle of how we use these chips. I should point out that everything is analog inside, but as soon as a neuron spikes, the address of the neuron, these neurons are labeled, the address of the neuron is converted into a digital word, and then the word is sent out as a digital address on an address event bus or using an address event representation. That's how we can use these lookup tables and these memory blocks. So we have the best of both worlds. We have analog, low power inside, and fast, asynchronous digital outside. And the inter-spike interval, the time between addresses, basically encodes the analog information. Remember, the frequency of the spikes is the way to encode all these analog variables coming inside here. So all of these are asynchronous. There is no clock. Everything is self-clocked. And all of the circuits inside are completely passive, meaning that if there is no activity, if I don't stimulate anything, everything goes to zero. There is no power being burned. And only when there is data coming in, they wake up and they start spiking, They start integrating and then spiking, and in doing the spikes, they burn a few picojoules. That's how we get a few microwatts. Remember the difference. We heard about tens of megawatts to run a 1-second simulation. In fact, the Jülich simulation, if you run for about an hour, it takes the power of all of Porto for a whole night. All of Porto, all lit up for a whole night, is 1 hour of Jülich supercomputer simulation. The platforms, there are amazing platforms that are being developed with Manchester and Heidelberg. Those are also high supercomputing platforms for doing very intensive simulations. And we heard they are about a kilowatt. And these chips are about tens of microwatts. So we're talking about 100 million less power consumption. So you can imagine, if you have a lithium battery, how many fractions of a second it takes on one of these supercomputing platforms, and how many months it lasts on one of these chips. It's really different goals, right? If you want to do evolutionary scale simulations and have faithful equation simulated, then you should use the high power consuming platforms. If you want to put these on scales in refrigerators to do processing, or on robots and have them, or on implants and have them run for months, then you should try to use these very low power architectures. And in fact, let me show you the latest chip that we designed. It's a 28 nanometer fully depleted silicon on insulator, for those of you that are technologists. It's a really nice process. It has 1 volt power supply, so it's really, really low power. And this chip has on-chip learning, so you can train on-chip with continuous learning if you have sensory data coming in. If my voice changes over time and I want this to keep on recognizing me, I can have the on-chip learning core adapt to the changes in my voice. And then I also have 1,000 neurons that are programmable. So if I want a recurrent network that always has the same dynamics and does not need to change over time, I can just program those connections in here. So there is 4 cores for programmable and 1 core for learning, and I can mix and match in the way I want. These are all technical details. There is TCAM, so content addressable memories. We heard about that. SRAM for other types of memories. The synapses are 4-bit. You can change the weight using 4-bit. There is a nice paper by the group of Karl-Heinz Meyer saying that 4 bits is enough, and they demonstrated with a really nice set of experiments that 4 bits are enough to simulate a large range and solve a large range of problems. They're really fast. You can go giga events per second. And you can scale. These are scalable. You can just connect the left output of one chip to the right input of the other chip, and you can just tile them together to build networks of arbitrary size. True North was mentioned. IBM True North is the chip that was designed by IBM. And because it's using the same process, we are comparing to that. And there is no magic here. We just did the chip after, and we learned with the True North designers are either our old students, my old students, or our colleagues, my friends. And they basically told me, avoid this pitfall, don't do that, this one, do this transistor bigger. And by just following all of these advice from them and putting in our own expertise, we managed to get more synaptic operations per second per watt. This is the measurement that was mentioned, the picojoules per synaptic operation. We can do 600 giga synaptic operations per watt compared to the True North one that is doing 46. It's less than 2 picojoules whenever you have a single spike coming in. We heard about biology doing it in femtojoules, and then the intermediate levels were about 2 nanojoules. This is the sort of in between those other platforms and biology. And also, whenever you produce an output, a spike, you also are burning a few nanojoules. That's because the output spike has to go and branch out and broadcast to all the destinations. And so whenever you have to broadcast to a large amount of destinations, you have to charge up these capacitive lines and then discharge them. That's why you burn more power than at the synapse level. So the synapse is a really tiny part that really charges up and discharges very quickly. It's still much better than True North. This is, just, as I told you, because we just followed their tips and our friends' tips. I want also to compare, we've been doing these chips since 1994. So this is just the latest one. There's lots and lots if you come to our lab, there is printed circuit boards everywhere in every corner with wires sticking out. There's lots of old chips. But the latest one is really nice. It's a really nice process, which is very expensive. It was like 90,000 euros to fabricate one of these chips, and we were fortunate that we got a EU project to pay for that. And if you compare our chip to like an old Intel by now, you'll see that you'll immediately notice a complete difference. There are processing cores and memory. This is the von Neumann architecture I told you about. Whereas here we have these neuron cores. The synapse is within each neuron. In the next slide, I can zoom in one of these and show you. But memory and computation is inside. There is no single bus going from the memory to the core and back and forth. Everything is basically interleaved and shared. The routing structure is here. So if you want to send a spike from one neuron to another one, you program this virtual wire by setting some registers here. So that's all of the routing is here, and all of the analog computation is in these blue boxes here. We can zoom in. I'll zoom in now. So if you zoom in one of these pixels here, you'll see that there is a neuron, which is a very small part here, and a synapse. And these synapses are these parts here. So if you look at the analog circuits, these are taking up really, I don't know, maybe 1/10 of the area. The rest of the area is used for memory. That's where we program the connectivity, the topology. Is this neuron connected to that other neuron? Is it connected back to itself? So all of this memory here is the standard CMOS memory. And this is the in-memory computing idea. And we are really waiting for these emerging technologies to come out. I don't know if you've heard about memristors, but as soon as memristors, resistive memories are available, they will be able to replace all of this. And this, this is like 12 transistors to implement 1 bit to store it permanently or not, as long as you have power supply. And a memristor, and I think it's like 20 by 20 micron. And a memristor is 10 by 10 nanometers. So we can really remove all of this part and increase the density a lot. We will be able to have hundreds of thousands of neurons instead of just 1,000 neurons on this 2 by 3 millimeter chip. It's really a tiny chip, and it has 1,064 neurons. So how do we implement all of these analog dynamics here? It's relatively simple. You just need 5, 6 transistors. I won't go through the details and explain you. If you're interested, I can send you slides and I can show you how the circuit works. But basically, whenever you send a spike into the input of the synapse, current flows through, it charges and discharges a capacitor, and in output, you have a current coming out. And this current has these linear dynamics. This is the output of the chip. This is the output of a real synapse. The time scale is the same, 10 millisecond, 10 millisecond. Here, in order to be able to see something on the oscilloscope, we had to increase the gain to nanoamps. Otherwise, the oscilloscope was not sensitive enough. But we could go down, and here, this is picoamps. So we are more or less in the same range. We can always go down to picoamps. It's just that it would just get buried in the noise of the oscilloscope. And by changing some of these parameters, we can change either the weight, like the response, the height, or the time constant of the synapse. So these are all analog parameters that we can change, and they can either be learned, or they can be set on the side of the chip. They can just be programmed. And it's so simple that you can actually derive the transfer function analytically just by writing the transistor equations, and you observe this. And if you fit the data with this equation, you get a very good match. So it's really not rocket science. It's really relatively simple subthreshold circuit design. And once you have this differential pair to implement this dynamics, you can start, this could be like a channel, a proteic channel. You can start putting together these blocks to implement neurons. And this is the neuron. You can see this is one block here, another block here. All these differential pairs that implement these dynamics with capacitors are used again and again to implement neural dynamics and synaptic dynamics. And now, so here we don't have these discrete activation of a spike generation with a step. We really use the physics of silicon to produce a smooth, exponentially rising spike, just like in biology, by using transistors as channels. So in this case, we would have activation channels and inactivation channels, like the sodium. You remember the sodium conductances. And then through this one, we have the potassium. And a single transistor is modeling a potassium channel, or a sodium activation and sodium inactivation channel. So just by doing faithful reproduction of the biophysics of real cells, we get faithful reproduction of the behavior. So again, we're not trying to implement abstract equations. We really want to reproduce the biophysics. And that allows us to have these picojoules and microwatts or nanowatts. That's just by using the physics of these transistors. So here it's, again, you can derive the equations. By coincidence, it turns out that our equation, by trying to maximize performance, minimizing power consumption, it turned out that we have an adaptive exponentially integrated fire model. If you remember those equations, you have this f here, and the f is a positive exponential. And you can fit the data with these equations, and you see you get a perfect fit. So it's really, really nice to be able to derive analytically from these transistors the transfer function, because then we can really know what we should expect from the chip. If you inject constant current into the neuron will fire, and it starts firing at different rates depending on how much current you have. If you turn on the slow variable, which is this green block, you push current into the capacitor from one side, you pull current into the capacitor from the other because of this negative term in the equation, minus Ig. And that gives you fluctuations. So any small thermal fluctuation introduces some noise. And people can think of this as a bug or as a feature. And we think of it as a feature, because if you need to do stochastic computation, you need to have noise in your system. If all the neurons in the chip are doing exactly the same thing, you will never be able to explore an energy landscape just by randomly looking here and there. If you have stochastic variability in each of these, then you will be able to jump, from one local minimum to another local minimum, and so on. So, and this is exactly what biology is doing. We heard about neural sampling in the previous talk. You can do neural sampling using this stochastic behavior here. And we take advantage of the fact that even though it's fully deterministic, every neuron is identical, it's a physical system that's subject to thermal noise and variability. So that's, again, something we don't fight against. We actually use it to our advantage. And this is an example of spike frequency adaptation, I told you. So as soon as you have an input to the neuron will start firing. If the input is big, it will fire with a very high rate. But then slowly, if you zoom in here, you see that the distance between spikes increases. That's this effect of, when you turn on a projector, you initially hear the sound, and then slowly you adapt away, or the smell, or other things. And you can do the same just by changing some of these parameters. So this neuron can become a bursting neuron, these bursts, like you have in the thalamus. It can become a regular firing neuron, like you have in the cortex. It could be a fast inhibitory neuron. It's the same circuit, you just need to change parameters to get different behaviors. So now I showed you how to implement these chips. I showed you examples of circuits to implement the neurons, the synapses. What can we do with these chips? Yes?
Can I just ask one question? In that specific case, it seems like the neuron or this behaviors induce some sort of saturation. So you're starting to have a slower peak rate. But could there be a situation where you actually have the opposite, where you start like slower and then you start speeding up?
Yes,
so
you can.
Both
so
ways.
That's with the synapse. The synapse here, it's actually a nonlinear circuit. So if you put the biases in the right parameter, you can demonstrate through also formally from equations that you can have this short-term facilitation, which means that the first spike will have a small jump. The second spike will have a higher jump, the third spike an even higher jump, which means that as soon as you have an onset, you start slow and you start becoming more and more sensitive to it. And so, again, by changing parameters, you can model what's going on in the motor cortex or in the auditory cortex or in the visual cortex, because there are neurons that do this in biology as well, and you can reproduce this.
So basically, you can replicate all sorts of low-pass, high-pass filters.
Yes.
Based on the
yeah, with some constraints, right? You cannot put any arbitrary cutoff frequency. There are some limits, but these are we designed it such that we follow the biology. Again, what we do in Zurich is we are doing basic research. So we want to understand how the brain works. So we do a bottom-up. We say biology has it. For some reason, it might be useful. We're just going to put it on the chip, and then we can see if we can actually take advantage of it. But whatever we observe in biology, we try to put it on chip as well, and then we try to see whether there is a functional role for that particular mechanism that we observed in biology.
And just one more quick question. Is there any interest in actually going beyond biology, in the sense that obviously biology has limitations, so there may be a biological reason for not speeding up your rates? But it may actually be advantages. It's just the fact that we haven't been able to do that biologically. If you explore that.
For example, one advantage of going faster is if you want to simulate evolutionary scales, like the setup that's being developed in Heidelberg. So you can have the benefits of the sort of biological plausibility and the principles of computation of biology, but then you can speed up. Here, if you just push more current, you just go faster. So you can also speed up here, but again, there are limits. Probably to do 10,000 times faster than real time, the best approach is to follow the approach that's being done in Heidelberg. And so here, it's really bottom up. We try to stay as close as possible to biology. We haven't been thinking about how to go beyond, because there is so much to explore, even just by copying, that we're still exploring that area, and we haven't thought about how to go after. But yes, so I showed you how to do neurons, how to do synapses, how to put them together in chips. What can we do with them? We can do all sorts of things. I'll focus on some. But if you want to learn more about the details, and I'll send you the handout so you don't have to write anything. There are papers that describe, how to implement learning with spike timing learning, how to do homeostatic plasticity. Homeostatic plasticity is a mechanism that keeps everything in balance. Even if the temperature increases or if I get fever, all of the parameters of the network are reshuffled around such that I don't go crazy. And the same happens with chips. If the temperature increases, if we wait for the summer and we have 10 degrees more, all of the neurons will start firing more. And so we have negative feedback circuits, which we manage to have time leakage rates, not time constants, it's not exponential, leakage rates of over 24 hours. And that's what we need to have homeostatic, because homeostatic is a negative feedback that pushes everything to stay the same. If learning tells us that we should change, and then homeostatic tells us, no, don't change, stay the same, then they interfere. So learning happens on 10 millisecond or minute time scales, and homeostatic plasticity happens on hours. In this way, they don't interfere, and everything stays balanced. So we have these circuits, which are really hard to get. 4 electrons per second through a transistor is really hard to get, but we managed to get those. We showed examples of supervised learning, unsupervised, inference, state-dependent behavior, perceptual bistability. I'll show some now. In fact, I should go quick. And then you can read more of the details through in those papers. So the first one I want to show you is learning. We talked about continuous learning. We have examples of continuous learning on chip that have been working for several years. In fact, we were inspired by Walter Sen already from 2007. Walter Sen is in Bern, and so either we go every once a month, or he comes once a month. We work together. And there's many other theoretical physicists turned neuroscientists that have been proposing spike-based learning rules that can work continuous time if you just deploy them in life. They've been also interested in understanding how biology works, but now they start to be useful for practical applications. If you want to deploy these things in cars, in refrigerators, then you want to keep them always on and have them always learning. And it's very simple, actually. They propose spike-driven mechanisms, so you still need spikes, but they go beyond the basic concept of spike timing. They look also at different variables, such as the membrane potential and the calcium concentration inside the neuron. And then they have different theoretical physicists have different variations of the same recipe. To a naive user like me, they all look pretty much the same. There is basically a region in which you should do learning, and another region, if you're out of these bounds, you should stop learning. That's how you have continuous learning, because if you get out of this region, you turn on learning again, and then as you're changing the weights, you go in the right region, you stop learning, and if the data changes, you turn on learning again. So all of these mechanisms are based on this very simple idea. And they have this prescription, which is very nice for circuits, because they tell you, you don't need to have 32-bit floating point. You can have a small number of states. In the extreme case, you can have 2 states, and it still will work. So that's perfect for us, because then 2 states, it's a very simple circuit, 4 transistors. Of course, if you have only 2 states, you need redundancy, because if all the synapses, you only have one synapse that has 2 states, you cannot represent a big number. You need many, many binary synapses to represent some analog number. And that's easy to do in VLSI. So we can really put many, many transistors on, and it's really compatible with the idea of being fault tolerant. Instead of having one very big, precise circuit, which will break if a transistor fails, you have many, many parallel, simple synapses, and even if 1 or 2 or 10% or 20% of those break, everything still will work. And it's been shown that you can degrade gracefully with these types of paradigms. And finally, you need stochasticity. This is a prescription from the theoreticians telling you that if you want to have a big capacity, memory capacity and computational power, you need to change only a random subset of the synapses with some stochastic behavior. If you change all of the synapses in the same way, it's just like having one big one. So you need to select a random subset and then change only that random subset. And all of these things are easy to implement in hardware. Even the stochasticity, which one would think is hard. How can you put a random number generator in every synapse? Well, we don't. We cheat. Instead of putting a random number generator at the synapse, we send in spikes with random timing. So you represent signals with frequencies. So suppose I have an input like a number or a visual pattern, and I represent that with 10 hertz. But every time I present these 10 hertz, the precise timing of the spikes is Poisson distributed. So the precise timing will be different every time I present the same stimulus. And that's the source of randomness. The difference in times, which still on average are the same 10 hertz, will be enough to be compatible with the theory that the theoreticians prescribe. And here is an example of how the learning works with the data from the chip, which matches perfectly the software simulations of Walter Sen and colleagues. So you have your input spikes. You can see they are Poisson distributed. They are not regular, but they represent some number, some variable. I think it was 50 hertz. And you have your output neuron, which is firing because it's being driven by many other sources of input. So we have 10,000 inputs per neuron. So this is only one input. Your neuron, it's doing its own thing. And whenever you have a spike, you check what's happening. Is the memory potential above or below some threshold? If the memory potential is above the threshold, then I should increase the weight. If the memory potential is below the threshold, I should decrease the weight. And you see it here. The memory potential in this case here, it was below, so I have a down jump. It's going down, and here it's going down, 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 and here it's going up, 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 up. So whenever the spikes arrive, I check, and I have up jumps or down jumps. And then I have also this bistability mechanism that tells me on long time scales, it's enough to have two states, this binary thing. So if I don't have spikes, the bistability mechanism pushes the neuron to a high or a low state. You can think of it as analog. As you're learning, your weight can assume any analog value. But once you stop learning, if you close your eyes, you stop rehearsing your poem, all of your synapses crystallize to either a high or a low state. And this allows you to be robust to noise. So this is really important. And then there is this stop learning part is here. You check what's going on average. The calcium concentration is basically the integral of your spikes. And if your calcium concentration is within some bounds, then you should learn. It means that your neuron is undecided. Is this a real cat or is it a dog? You don't know. So change the weights. And if then the weights change in a way that it always pushes the neuron to fire, yes, it's a cat, I'm positive. So then it's going to fire at a very high rate. The calcium concentration goes above. Then you say, OK, stop learning. You got it. If you're sure it's not a cat, then the neuron will just be silent, and the calcium concentration will also go below bounds. And also in that case, say, OK, you're not the cat neuron. Someone else is the cat neuron. Don't change your weights. So this is how you have continuous learning. You can just have it on all the time, and then if this neuron becomes the cat neuron, it will start changing its weight whenever it sees something and it's undecided, and it will stop changing the weights when it becomes the expert in either recognizing or ignoring pictures of cats. And we can apply this now to our chips. This is a circuit on the chip. This is a single synapse. We have thousands of synapses. We can put them on. We can do the standard benchmarks. We saw this MNIST benchmark. Basically, you show a bunch of handwritten digits. You train the neuron to recognize all the threes and not recognize all the other characters. And the same for all the other digits. You convert everything into spikes. If it's white, it's no firing rate, or maybe 10 hertz. If it's black, maybe it's 100 hertz. You send it to the chip, and then you let the algorithm increase its weight or not. In this case, it's supervised, because whenever you send class 3 to the chip, you also make the neuron fire such that the calcium concentration goes in the right region. If it's another digit, if it's 0 or 2 or 4 or 7, you make the neuron shut down. You inhibit it such that it does not learn to recognize the other digits. So here it's supervised. And after you do this, you get, of this single neuron, you get an output recognition rate, which is around 32%. And if any of you have ever done this MNIST benchmark, you will start laughing, because the machine learning guys that do MNIST on GPUs, they are fighting with 99.92% and 99.95%. Anything below 99.9 is just laughable. It's just, you know, out of the competition. So here, this is irrelevant for them. It's, you know, it's useless. We were very disappointed. But then we went back and looked at the literature, and we found out that, you know, first of all, our neurons are analog. So every neuron is slightly different from every other. So even if you send the same input to all the other neurons, remember, we have a row of neurons, they will behave in slightly different ways. So we can call these, instead of crappy classifiers, we can call them weak classifiers. They don't classify very well. And then we have many, many independent weak classifiers because of mismatch. And fortunately, in 1995, Shapiro et al. Showed that if you have an ensemble of weak classifiers, the overall consensus of the ensemble can be better than the consensus of a single, or the output of a single classifier. And in fact, not only that, the error goes down exponentially with the number of weak classifiers. And that's what we did. So we said, let's test it. You know, we connected the same input to all the other neurons. So here it was 2, then we went to 8, or maybe it was 4, 16, 32, 64, and so on. And we saw the classification performance increase. So I don't know if it's following this exponential, but we were just happy that it was increasing. So you can imagine that if you have enough neurons, in this chip we only had, I think, it was 128, but we were using the others for something else, so we stopped here. But you can imagine that now you can become competitive with the state-of-the-art of MNIST. And if you have enough neurons, you can start to reach, you know, 98.4% or 85%. And you can do this with any input. It doesn't have to, anything that can be converted to spikes. So if it's visual signals, you convert those to spikes. If it's auditory signals, you send them through a filter, like a cochlea filter. You look at the frequencies and you convert those to spikes. You can combine, you can have retinas and cochleas sending in. And then you can try to recognize the combination of the word 3 and the picture 3. And you can imagine, you can do all sorts of nice tests with these chips. And I should try to hurry up. I'll show you some examples. Before I show you the examples, just one atom of computation. Now that we have these chips, we have learning. That's how do you program, like a kid, to carry out a task? You know, set the table or wash the dishes. You show them, you train them. So learning is useful for programming these neural networks. But also, how do you do conditional branching? If, then, else. If I see this input and I have this internal state, then do this, otherwise do that. That's more complicated. But we found a way of doing this state-dependent or context-dependent computation. And we found the computational primitives that allow us to do that. And those are these winner-take-all networks. It's a network of neurons that's connected with excitatory connections among each other. Every neuron excites every other neuron. But they are also connected to global inhibitory neurons. So let's do it here. So every neuron excites its nearest neighbor and its second nearest neighbor. But every neuron also excites an inhibitory neuron, which inhibits everybody back. So we have both positive feedback and negative feedback. The positive feedback alone would just make everything explode. But the negative feedback is there to keep everything in balance. And now if you apply this configuration, which, by the way, has been demonstrated to be in visual cortex, in auditory cortex, somatosensory cortex, olfactory cortex, this type of excitatory and inhibitory, here you see pyramidal cells, you see basket cells, inhibitory cells. So this type of circuit, which has been very, very much simplified here, is present in all parts of our brain. And you can imagine why, because this circuit is really powerful. It can do both analog computation and digital. It can act as an amplifier. If you can apply gain, so you apply an input signal, the output is going to be an amplified version of the input. It can act as a digital switch. If you have two inputs and one is slightly bigger than the other, it can select, like a flip-flop. It can act as signal restoration circuit. If you have a noisy bump in input, the output will be a smooth bump. So it's really a useful computational primitive that can be used everywhere. And in fact, nature, as soon as nature found it, if you look at the evolution of brains, as soon as cortex was developed, then there was this big discontinuity in the size of brains. It started growing like crazy. It just started copying cortical circuits everywhere. And in fact, this is what we do in the institute. We study these cortical circuits. So the anatomists and the neurophysiologists study the neuron. This is, again, a pyramidal neuron, which is receiving input in the green, and it's sending output in the red. And it's been shown that you can, by having these layer 2, 3 cells, basket cells, layer 5, 6 cells, you have these type of winner-take-all mechanisms. And I just want to show you an example of the chip, how it works. So what we do is we have a bunch of neurons on the chip. All of the neurons are connected with each other with these positive connections, and then they all connect to the last 4 neurons on the chip, which then inhibit everybody back. And you can see what's happened. If the blue dots are the inputs and the black dots are the outputs, you see that as soon as you provide an input, everyone fires. They all start to fire, and they start to excite the inhibitory neurons. There is dynamics. It takes some time. The inhibitory neurons integrate these inputs, and eventually they start firing. When they start firing, they inhibit these back. So they shut everybody down. But the winner, so this one was receiving slightly more spikes on average than the other one, this population of neurons. So the winner recovers and then activates the inhibitory neurons, which then shut these neurons down. So you can see this winner-take-all mechanism. It's selective amplification. It's amplifying the winner and suppressing the noise, the distractor, the loser. And I show you a video of this live, with real-time behavior, if I can find the mouse. I can't. There it is. So let me explain to you what's going on. The top is the input, the bottom is the output. So here I'm sending 2 bumps. And for the first half of the experiment, I send stronger activity to the bottom bump. And then as time goes by, I shift the activity. I make the bottom bump become the loser and the top bump become the winner. So if you look at this, you should see over time, this is very dark and this is not so dark. And this will become darker here and this will become gray here. And here you will see the output. So the output should select a winner. There's always either one or the other, with its own internal dynamics. It's a dynamical system. It's not like a flip-flop, a max. And so here it's just going. I'm stimulating. This is, you can see if you had the chip here, you could just see it as data was going through. These neurons are stimulating both. Both are stimulating the inhibitory neurons, which inhibits everyone. Because this is stronger, it's winning. But now, more or less, they should be more or less the same activity, the same heights. And now this one's slightly bigger. So you can see clearly, even though this is sort of noisy, here the output is much more clean. And you can see a less noisy bump. Here you see there's lots of jitter. Here's less jitter. So it's doing signal reconstruction, selective amplification, suppression of noise, all of these things with just one very simple circuit with one simple connectivity, which happens to be everywhere in our brain. It's a remarkable thing. And in fact, the circuit, you can use it to explain perceptual bistability. If you stare at this long enough, your perception will switch. Even if you don't want it to, you don't have control of that, and it will switch with a gamma distribution over time. If you present it to the same chip, the one that I showed you before, with the same type of connectivity, the output of the chip will switch. These are spikes, and these are the 2 populations. So you can reproduce what people measure in monkeys just by using the chip with the same dynamics. We didn't engineer anything into this. We only put the same time constants, the same dynamics of the synapses and neurons, and we observed the same overall perceptual behavior. And you can use it as working memory as well. So you can send an input, make that win. If you take the input away, it became an attractor. It will, even after the input is not there, the average activity of that population will stay high. As soon as you send another input, because of the winner-take-all part, it will make the other one lose. It will stay, et cetera, et cetera. So this is working memory. It's like if I give you a telephone number, you will be able to remember it even after I stopped telling you the numbers. And this is probably the circuits that are going on in your brain that are allowing you to remember those numbers for some time, for some minutes. Let me move, I'll skip this neural state machine part because time is running out and just show you some videos to show you what can be done. If there is interest and someone asks the question after, I can show you the Sudoku. So you can use this to solve constraint satisfaction problems. It was mentioned Sudoku. So there is a video of Sudoku, which I can show you in question time. But what I want to show you now is that you can actually connect these chips to robots. And you can, I told you it's important to have this closed loop behavior. And this is what we do. We basically have a silicon retina, which is producing spikes. These sensors are really like real retinas. If you show, for example, a moving dot that's in a circle that's rotating, you will get spikes that form this spiral over time. So in terms of the output of this camera, it's really crappy. You have very low resolution. This is a car scene. I don't know if you can see, but these are cars and trees. This is the output of the retina if you just take a snapshot. Only a few spikes are firing at any one time. But over time, it's very high resolution. Every microsecond, you get a spike. So you know exactly what's going on because you can integrate over time. So now we have this retina on a robot which is moving around. We send the spikes to the learning chip. This is the chip, which is basically an array of neurons with all the synapses. We connect the various populations of the neurons to the motors, and we have this behavior, this closed feedback loop. How do we connect things to the motors? What do we do? This is the way everything is connected. The retina is looking at the environment. If we have any activity on the lower part of the retina, we send all the spikes that are coming from one side to a population of neurons, which is going to tell the robot to turn left. Any spikes from this side will go to a population of some neurons that will tell the robot to turn right. And this is what's happening. Basically, these are telling the motor neurons turn right or turn left, and then they're telling the other motor neurons don't turn left or don't turn right. So if I'm saying turn right, at the same time I'm saying don't turn left, and vice versa. I also stimulate a population of neurons which is saying go fast. And if I see any activity here, I inhibit with minus this go fast. So I say slow down. And then you can look at the output of the spikes, and then you can drive the robot. It's a very simple network in which I connected the populations of neurons together. It's populations of neurons, because neurons are noisy, so we need to have populations. And by having these negative connections, positive connections, connecting speed neurons to left and right neurons, you can observe what looks like intelligent behavior. And here, this is a picture of the robot going this way. I'll show you now a video. But the robot is moving around, and here's the average activity of the various populations of neurons. So when you're at position 1, you start to see some activity on the left side of the retina, which activates the obstacle population. This obstacle population then drives the turn population. And then the robot commands go to the robot saying turn. On position number 2, you're at the peak. You see everything on the left, the maximum activity, it's turning even more. And position number 3, you're away, you don't see anything anymore, everything goes back to 0. So if you have this running, you can see the robot moving around and the various activity of the retina and these populations turning on and off. And you can see that it speeds up and slows down if it sees things on the left, on the right. It's a very uncontrolled environment. People are walking around. You have edges, shadows. So you don't need to calibrate for the precise amount of light and the colors. It can go under tables. It's really very, very simple, activity-driven, just by neurons, robot. Again, here there is no computer. There is only a silicon retina, which sends spikes to a neural network, which then controls motors. No computer in the loop. Everything is driven by spikes. And if you were to miniaturize everything and put everything on a single package, it would really be microwatts. So it could run for months and months with just a lithium battery. Of course, the motors are the ones that are burning most of the power here in the robot. So yeah, you can see how it really can get out of really difficult situations just because of this neural network The same thing, if you're interested, if I have like 2 more minutes, I have another video to show. You can do convolutional neural networks. Now it's very popular, for example, for recognizing cats and dogs. We can do it also at a very simplified level with the silicon retina. The silicon retina, I told you, it's not a very high resolution. It's really kind of a crappy imager. But the nice thing is that it produces events as they happen. As soon as something changes, you get the output within microseconds. So what we did is we connected the retina to the chips, and then we trained the retina to recognize different symbols. In particular, the demo we have is we're flipping 50 cards. This is actually Bernabe Linares Barranco. He's a colleague of ours that collected the data set. So we go, in 2 seconds, you have 50 cards going through. The retina is looking at all of the spikes produced by all of these symbols. You see it here. These spikes go to a convolutional layer through kernels. The kernels go to a pooling layer, which basically converges everything. You try to understand what's going on. And then these go to an output layer, which, depending on how the spikes are routed with the weights that are set, it will tell you which population is firing most. If it's the heart population, the club population, the diamond population, or the spade population. And you see it here. So these, you will see in the video, these are the silicon retina outputs. Now it's on a 2D plot, you can see them like this. On a 1D plot, they're just a bunch of black dots. These go after 8 milliseconds, the feature layer starts to fire. After another 8 milliseconds, the pooling layer starts to fire. And after 10 milliseconds, you have the output. It tells you this is spade. In order to make it easier for us to figure out what's going on, we rearrange the cards so that it's always a sequence of hearts, diamonds, spade, clubs, and so on. It's always the same sequence, so we can test whether it's correct or wrong. So you'll see now in live what's going on, and you can see why it's really nice. By the way, if you had a normal camera, it would take 30 milliseconds to capture one single frame. Then you have to send it into the convolution layer, then to the pooling layer, and so on. Here, after the first spike, after 8 milliseconds, you start to have the first convolution outputs. After 8 milliseconds, you have the pooling, and after 10 milliseconds, so after 26 milliseconds, you have the output, even though the input did not finish changing yet. So within the time of taking one frame with a normal camera, you already know the output through this very fast, low latency chain of spike processing. And again, there is no computer. There is no clock. There is no camera. Everything is spikes, and it's spike-driven. And if you don't have spikes, as soon as you stop, you don't burn any power. And as you have the spikes, you're burning a few microwatts. So that's the real time. And here you can see the population of neurons. And this is just, if you had the chip here, this is what you would see. It's just real-time data going through. So just to show you again. I don't know, maybe I need to do this. Yeah, so this is just an example of how you do these behaving systems with these chips with microwatts and connecting them to robots, sensors, and actuators. So the overall goal of the whole area of research, not only in our institute, is really to try to close the loop by doing modeling and looking at neuroscience, looking at real brains, models, building chips, building small chips. We're not in the race of building 1 million neuron chips. We want to be fast and agile and be able to change ideas and technology. So every 3 months, we can send out a new chip. And then we can put these small chips on robots and then close the loop and, okay, say, this architecture doesn't work. This learning mechanism is not good. Let's do another round, and we can do this round. So the whole goal is really to understand the principles of computation by testing them with real physical systems that reproduce the physics of real brains. Yeah, so this lesson that Carver Mead used to tell us, listen to the silicon, really use the physics of silicon to do what you want to do. And let me finish by just acknowledging the various funding organizations and the Institute of Informatics. And thank you for your attention.
Thank you, Giacomo. So questions from the audience?
Thanks a lot. Are there any Well, there must be some. What are the mathematical challenges in terms of models that you're facing right now? Because I know that neural networks has a lot. There is a lot of heuristics and a lot of things that work just because they work. We don't have a theoretical explanation for that. What are the ones that bother you the most?
Yeah, so within this institute, we're interested in understanding how the brain works. So the modeling part is really a very big part. The hardware design part is only 1/3, and 2/3 is doing experiments and modeling. And so we're interested in context-dependent computation. If you're thinking of cognitive behavior, you need to have learning, but also state-dependent computation. And the models that we're looking at are using these winner-take-all networks to do, implement state machines, neural state machines or finite state machines. The other is, of course, memory formation and learning. So we're looking at hippocampus, and we're trying to implement models of hippocampus so that then when we have a robot moving around, we can make it recognize a sequence of past events or produce a sequence of desired motor events. If I am here and I want to go to the kitchen, I know that first I have to turn left when I see this symbol, then I have to turn right when I see this other symbol. So we're looking at the models, the literature, but also we're validating and invalidating them with these real-time behaving platforms. And finally, the last one is we're looking at temporal dynamics. So sequences, if we want to process temporal sequences coming in, for example, EEG, EMG, ECG, what is the structure of the neural network that will allow us to recognize that, 50 milliseconds ago, you need to have memory over time. There was an anomaly in my heartbeat. And how can I have a network that, as the heartbeat data is going through, without having to store it on a computer, in real time can tell me, something's wrong. These are recurrent neural networks in which you have to train the recurrent weights, which is really complicated. There is a lot of activity going on in the computational neuroscience literature. We are trying to see, out of all those models, which ones survive when they are implemented with noisy, variable, and low-resolution neurons. So this is, again, a way of mainly invalidating models being proposed, and maybe then we find one or two that work. And then we can say, in biology will have the same problems. It will have low resolution, it will have variability. So out of all these 12 models, maybe these 3 are more realistic. And then we can tell neuroscientists, can you go and test, maybe if you turn off calcium or if you block all inhibitory neurons, you will see whether it works better or not. And so the idea is really to close the loop with biologists, taking input data from neuroscientists and computational neuroscientists.
So during your presentation, you talked about the cost of producing one of those chips and the time to produce one of those chips. Do you ever thought or are using FPGA to avoid the cost and the time to wait for a silicon?
That's the question. Why do you go to this business of building chips at all? That was the very first slide. We want to use the physics of silicon. So if we want to use the physics of silicon, we have to use these subthreshold analog circuits. And FPGA does not allow us to do that. So there are colleagues of ours that are using FPAAs. So they designed field programmable analog arrays where they can do this, mainly at Georgia Tech. But as I said, whenever we need to do a new chip, it doesn't take us a lot of effort. It's a few months, 3 months work, and then you have to wait for 2 months. So within a PhD, you can do 2 or 3 chips, 2 or 3 cycles to try out your ideas. So,
Hi, very nice talk, thank you. Just a question, more a conceptual question from someone who's not really in the field. I mean, you mentioned that you are inspired by the brain in order to produce your models. I was thinking that the brain is not only neurons, but there's a lot of glial cells. And microglia, for instance, is important in pruning astrocytes. They can actually make synapses in the hippocampus with around 2 million synapses with neurons. And they are important integrators of energy. They can actually change volume in the brain. They can actually connect very fast through myelination, for instance, other parts of the brain. And in none of these models, these are very neurocentric models, actually, is anyone inputting these kind of non-neuronal cells that are actually critical for the work of the brain into these models?
Yeah, so we are very much aware of the role of glia cells and then the regulating role and various roles also in plasticity. we are making compromises. So if you notice, all these neurons that I talked about, they're point neurons. There is no 3D structure. There is work being done also within the institute and outside on doing compartmental models where you have multiple dendritic branches. But then adding also the effect and the role of glia cells is something that would probably increase the complexity even more. So we are trying to grow, but slowly, and so this is something we are studying and trying to understand by just studying the literature, but putting them on silicon is probably 2 or maybe 5 years down the roadmap. It's not yet something. Plasticity is something really important, but we've been changing weights, but you know, like you mentioned, myelination, making axons thicker or longer or faster, that's a really important form of plasticity that we are also not taking into account here, that we would really love to be able to take into account. But at some point, the time is what it is, and we have to make some...
Maybe actually the problem with energy in the brain. So the brain without glia consumes much more energy. So one of the possibilities, conceptually, that actually you need glia in order to actually manage local energy levels.
Yeah.
Glia, of course, can modify the flow of the blood into specific regions, and the purines can regulate ATP levels. And we know that actually in disease, where actually glia are perturbed, the energy levels, it's by PET scanning and other techniques, patients have much more high energy levels.
Yeah.
I think it's important to...
Oh, absolutely. And we've been involved in proposals that unfortunately were rejected in the EU proposals, where we did try to propose to study and combine circuits that model the effect and the role of glia in signal reconstruction, in healing possible areas of the chip. So we are aware of it, and we really like the idea of being able to implement them in hardware. We're just either waiting for the funding to come or the time to be able to investigate those.
So unfortunately, we don't have more time for questions now, but you can ask on the coffee break. Now we have the visit to the museum, and guys, please also don't forget about the hackathon. Okay, the board is waiting for you. Okay, so let's thank again Giacomo.